Welcome to my talk on the Jumpstart Guide to Deep Learning in Audio. And my name is Wilczek. And I just wanted to ask you, who in this room has ever trained actually a neural network for audio? Okay, awesome. And who has never ever done anything like this? Perfect, because this talk is for you, actually. That's the outline for today. First, I would like to maybe say a few words about why it's interesting maybe to learn deep learning for audio and to apply it. And then I would like to delve into what actually stops people for even starting. And when we're past that, we can talk about what really concrete steps you could take actually today to start learning deep learning for audio. And then even to speed up this process, I will give you an outline of just the most important terminology in deep learning, and we'll hopefully conclude with a live demo. Just a few words about the slides and code. These are available on GitHub as a private repo, I guess, but after the talk, I'll make it public. And whichever questions you might have, please wait with them until the end of the talk. There will be 5 to 10 minutes for an Q&A. My personal mission is always to lower the barrier of entry to audio programming. And I try to do this by writing high-quality articles on my blog and publishing high-quality videos on my YouTube channel. And this talk is also a part of this in the sense that I'd really like to lower this barrier of entry into deep learning for audio. I'm also an audio developer at Loudly in Berlin, where I'm responsible for the musical features of the Music Maker Jam loop-based music app. And this app is also cool for me in the sense that it also lowers a barrier in the sense that you don't need any musical background actually to be able to go into the app and on your iOS or Android device and actually create high-quality music. And on the same note, we have a different solution for video editors that actually also simplifies their workflow significantly, where you can just upload your video and then pick and choose a track from a rich catalog of music. And you can even customize it in real time and then simply export it and upload it, to YouTube, TikTok, or any other platform. And as a final introductory note, I just wanted to say why I feel eligible to give this talk, because exactly 1.5 years ago, I was in this position of a complete beginner, even a skeptic in deep learning. And I've gone through this path when 2 months ago, actually, we published a research paper at the Digital Audio Effects Conference in Vienna, which I think is one of the largest such conferences in the world, which is exactly deep learning applied to audio, applied to virtual analog modeling. So you may say that my background in this area is already peer-reviewed. Just to clarify what we mean by deep learning. By deep learning, I mean a subfield of machine learning which uses data to solve problems, but it assumes that this data has some hierarchical structure in the sense that more high-level concepts consist of simpler, lower-level concepts down to the very input that we give to it. In this example, there's a problem of labeling an image, which objects are there, and it can be solved by learning so-called intermediate features, right? So is there a person in the image? And how to determine if there's a person? Well, maybe there are some curves in the image that may indicate that it is a person. And it goes down to a very low level, you could say, which are the input pixels. And this is a deep hierarchy of concept, and hence we call it deep learning. And now, there are a few reasons why you may want to consider applying deep learning to audio. Some are maybe better than others, but I really believe now that there are some areas in which deep learning can provide significantly better results than non-deep learning methods without a lot of mathematical complexity, for example, which is present in very complicated digital signal processing models. But also, we can apply it to completely new areas that wouldn't be possible outside of deep learning. And here I listed a few examples, you could say, where deep learning is used. As a particularly interesting example, And this research paper, the authors, as you can see in the image, they trained a so-called autoencoder network to learn a so-called semantic space of synthesizer parameters. So now imagine a synthesizer, right, where you don't just have an LFO control knob or filter cutoff knob, but you have a knob that says, okay, I want my timbre to be more aggressive, right, or darker. And that's a very interesting and creative application for the end user. Yet, although it's so interesting and appealing, there are still a lot of people who are very confused or terrified of even starting. And I fundamentally believe that there are some myths that stop people from even starting. And the first step is actually to debunk these myths. So the first myth is that learning deep learning is hard. And I fundamentally disagree with this statement, because out of many areas of computer science and digital signal processing, actually deep learning is one which has the largest number of high-quality, online, free knowledge sources that you can draw from. And not only this, but unlike many areas of digital signal processing, it has great software support, also with huge communities of people who ask questions about this software, like, for example, on Stack Overflow. And then, as you can see in the plot, there is a huge body of research in deep learning that's constantly growing. And, well, my approach is that if there is actually so much published in this area, then it cannot be impossible to learn, right? And as an even more inspirational example, I've done an interview with a colleague of mine who actually not only self-taught himself audio programming, but also deep learning without any prior background in this area at the university. So he's a trained musician, he's a professional musician, and yet he was able to pull it off. So I hope this will be some inspiration if you are afraid of failure. And myth number 2 is that you need a lot of data to even start with deep learning. And fortunately, another colleague of mine, Alec Wright, has proven in his published research that for some problems, even as little as 1 minute of training data may be sufficient to achieve quite good performance. And not only that, but actually the best research papers, they not only publish their code, so you can check it out on yourself, but also they share with you their data sets. And you can freely use these data sets, at least for your education, right? So I will try to give you a very good source of data that you can use actually for learning. The third myth that stops people from even starting deep learning is that, okay, I need a computational cluster. And that is also not true, which I hope to prove in the live demo today. We can actually use local GPU to train models, and published research suggests that some audio deep learning models are even faster to be trained when optimized properly on a CPU. Well, of course, if these are not options, then you can always turn to some computational clusters available that have some free quota. So I'm not recommending these platforms, but I'm just saying that they are available. And finally, still some people believe that deep learning models cannot run in real time. And of course, it is a challenge, but the sole proof that there are commercial plugins which use deep learning contradicts this myth. And there are a number of techniques for improving the performance of deep learning. And one of them, for example, is pruning, so reducing the network size, which is the largest bottleneck when running them in real time. And there are also efficient computational libraries available that you can use to help you. So now that you understand why it may be interesting to learn deep learning, and you believe that it is actually possible, I'd like to outline my proposition of the 4 steps that you can take to start from scratch. And of course, I love learning from books. I love books. And so the first step is to read a book, which is called The Deep Learning Book by Ian Goodfellow, Yoshua Bengio, and Aaron Corville, which is actually available for free online. But it's not only that, but also the authors are very understanding, and they they created the book in a way that is very approachable to the point where they say, okay, if you want to learn deep learning for practice, for industry practice, and you're not interested in deep learning research, here are the chapters that you need to read, right? And that saves you quite a lot of time. To somehow complement it, I recommend watching a free YouTube lecture on deep learning. It's another great resource. Here I listed 2 examples. I can recommend personally the one by Alexander Maya from my university. And what is great about these lectures, unlike in-person lectures, that you can watch them at twice the speed while you're doing your chores. And I recommend really making notes while you're listening to them so that you learn this vocabulary in deep learning, because that will allow you not only to communicate to other researchers, but above all, Google for stuff, right? It'll be easier to find. So now you read the book, you watch the lecture, you have this deep learning basis, but it's not specific to audio. So to put this audio layer on top of it, I recommend reading these 3 free research papers on deep learning in audio. Of course, there are other papers that you may read. I just found that if you have this deep learning basis, these papers actually guide you step by step how you can apply the same methodologies, but for audio. And the 4th step is that you can train your first model using these free tools I recommend. So the Python language, PyTorch library, the IDE of your choice, so PyCharm or Visual Studio Code, then your local machine, and finally some ready-made architecture and dataset from GitHub, which are also links to in this presentation. Now, as a kind of interlude, I have a question to you. Like, what do all these 4 steps have in common? I really try to make it visible in the slides. Do you have any idea?
They were free to access.
Perfect. They are free. They require exactly 0 cost whatsoever, just machine and internet access. So there are literally no excuses not to start. With this out of the way, we can pass to the part where I'd like to outline some of the concepts that we'll need for the live demo later on. And we'll start with machine learning. What we understand under machine learning is that we deal here with algorithms that are expected to improve the more data we feed in, right? We probably heard this, the more data, the better the performance. So machine learning has this crucial assumption. And deep learning draws on it, saying what we said at the beginning, right? So we use data, but we also assume that this data is somehow structured in a hierarchy of some kind of concepts, and this constitutes the deep hierarchy of concepts. And of course, this adjective deep can also refer to deep neural networks, so like these 2 explanations are possible. And the fundamental idea in deep learning is the idea of a dataset. In the context of audio, a dataset may range from a few minutes to a few hours to hundreds of hours of audio. And what we need as an input to our network are either raw samples, so simple samples of our wave file, or we can compute some features out of them. So for example, a spectrogram is a feature. Mel frequency, Kapstar coefficients are also example of features. And when we have this, then we may divide our data set into so-called examples. So in supervised learning, we have this concept that the data set consists of examples. So the input to the neural network and the desired output, the so-called target. And we have this input-target pairs, and they're like a good material for the neural network to work with. And when we have this whole data set of examples, then we split them. We split them typically into 3 subsets. The first one of them, which is typically 20% of the whole data set, is called the test set. And the test set is something that should ideally tell us how our algorithm would perform in the real world, right? So we will have some algorithm would like to deploy to the real world, but then it's already too late to see if something's wrong. So we need some kind of surrogate to see how our algorithm would perform, and that's what test set is for. The training set, on the other hand, which is the 80% of the 80% of the whole data set, is the set that our neural network sees during training. So this is used for training, and neural network uses it to update its parameters. And then there is the validation set. The validation set is used not to update the network parameters, but to inform us what are the learning dynamics. So is the network actually improving on previously unseen data? This will become more clear later on. And here's an example of how such a dataset could look for a virtual analog modeling problem. Virtual analog modeling deals with taking analog audio effects, analog circuits, and modeling them with software. So here, as a data set, we could have an input signal which could be 10 minutes of guitar and bass recordings, and the desired target signal, we run it through the circuit that we want to model, for example, a distortion circuit, and we obtain the output. So now we have matched, right? We have the input signal and what would come out of the effect, the desired, the target signal. And then we can split it into the data set. And here's like 20% of 10 minutes is 2 minutes, and the same for training set and validation set. As features, we'll take raw samples, and we have, in the training set, we have these examples. So we'll say that each of them will be half a second length. So each example is half second of input and half second of the corresponding target. And now we group these examples into so-called mini batches. And the mini batches is the idea that when we have a training set and we are in training, we run this set through our neural network, then we don't want to process the whole set in parallel, all the examples in parallel, but we also don't want to process them one by one. So we perform this grouping into mini batches, and it is said to have better learning dynamics. Okay, we have our data set. Now let's deal what actually is a neural network. And mathematically, it was proven that actually feed-forward networks are so-called universal function approximators, which means that given enough width or depth, such a neural network could actually approximate any mathematical function. And we, as a DSP engineers, could think of it that actually a neural network is a kind of input to output mapping, right? We input some data and we get some data out. And this sounds a lot like a simple filter, right? And exactly, here we have an example of a neural network. And if you look at it, on the left-hand side, we input our samples, right? These are raw samples. Then we perform some mathematical computations on them, and we get a sample out. And this is nothing new. This is an FIR filter. The only difference is that now we have the weights of the filters that we can update. And these middle layers between the input and the output perform the following processing. So we have the output of the previous layer. We then multiply it by some matrix of coefficients. We add to it the so-called vector of biases. And then we have a vector to which we apply element-wise a so-called nonlinearity. And we have the output of the current layer. And that's how this propagation follows. And what's important here, that this nonlinear function is something that we choose ourselves as human operators. It could be, for example, the tanh function. But this matrix of weights and vector of biases is something that gets actually updated during training. So if you hear that we're training a neural network, it means that we're updating the weights in this matrix and the values in this bias vector. Okay, so if this is an FIR filter, this is a feed-forward network, like, is there an IAR filter? And it turns out that there actually is. In neural networks, it is called a recurrent neural network. And it is based on the idea that when we process the current input, we also input the previous output of the network, right? To calculate the current output of the network. And we store the current output of the network in a buffer for subsequent iteration. And here is an example that was actually applied to audio in a paper published by a former employee of Native Instruments and currently with Python. So it actually works. And here's one example that I don't want to go into too much detail, But this is a neural network that we'll use today in the live demo, which was widely successful in audio. And this is remarkable because, as you can see, it was invented 25 years ago. So entirely before deep learning was fancy. That's very interesting. We had these networks, right? We had this data set. And now what happens when we pass our data through the network? We have some output, and we typically denote it by, do I have a mouse here? Yes, by this y hat. But now we need to say, okay, like that's the output of a network. How far is it from what we wanted to obtain? And here comes the idea of the loss function. The loss function basically tells us how far are we from what we wanted to achieve. And a very simple one is this mean squared error. But the problem with audio is that it's perceptually relevant if the same absolute change happens when we have a low signal amplitude or do we have a high signal amplitude. So it's better to take into account actually the energy of the signal that we are processing. And that's why, for example, we use this error to signal ratio. And the capital N here is the size of the mini batch because we average over the mini batch that we process during training. All right, we had our data set, we have our neural networks, we process the data through the network, and we can calculate how far are we from what we wanted to achieve. How do we now, on this, update the network? We do this by calculating the derivative of the loss function over each and every weight parameter in the network. So it's a mathematical operation that is done on a computer. And that allows us to compute a so-called gradient. A gradient is a very cool vector because in the parameter space, it shows us the direction in which the loss function is increasing, right? But we do not want to go in that direction because we want to decrease the loss function. We want it to be as small as possible. And that's why we take a step in the parameter space in the negated gradient direction. And now there are a number of ways how we could take these steps. And one of the most popular ones is called stochastic gradient descent. But the thing is that here is a very good area to introduce a lot of tweaks. So we can do it somehow predicting, how the steps will improve the behavior and so on. So one of the examples that I recommend using of this stochastic gradient descent with tweaks is called Adam. And what is cool about it is that, again, like this computation of the gradient, this Adam algorithm is already implemented for us in software. So we don't need to deal with this. And that's really powerful when it comes to applying deep learning. And then comes the idea of hyperparameters. And hyperparameters are everything that is set by us, so the human operators, and not change during the learning procedure. In the sense that when we have this gradient update, the network's parameters change, but hyperparameters don't change. And this is an area that's actually very challenging in the sense that you need to have experience and knowledge to be able how to change these parameters to achieve better results. And what I wanted to point you is that one of these parameters, hyperparameters, is the architecture of our network. What it means that when we decide on a specific architecture of our network, we already made some design choice. We already fixed something. And now it is one of the things that maybe we can improve upon. All right, with all of these concepts out of the way, we can now proceed to training our neural network. And this is done in a way that we train in so-called epochs. One epoch is an iteration in which our neural network sees all of the training set. We have more of these epochs, sometimes 100 epochs, and in each epoch, our neural network sees the whole training set. So in each epoch, we step through each mini batch in the training set. So we have our data set, we have our training set, and we have mini batches in the training set. So for each mini batch, we run it through the network, we get some output. Based on this, we calculate the loss function. Then we calculate the gradient of the loss. and then we update the coefficients. And so it goes. And when we're done with an epoch, every few epochs, we may want to run a validation set. And we don't calculate the gradient. We just look at the loss function to see how our network now performs on unseen data. And if it's maybe better than the last time we calculated the validation, we may want to store the network parameters. And when we're done with all the epochs and all the validation, we can now adjust the hyperparameters and say, okay, maybe we should increase the size of the gradient step, the learning rate. Or maybe our architecture is completely useless, we should get rid of it. And when we've done this decision to change a hyperparameter, then we need to repeat the whole process. And finally, when we are satisfied with our network, we adjusted it according to our validation set, we can evaluate it. And for this, we can use the same loss function or a different loss function. And this will give us simply a number. And this number allows us to compare against our previous approaches, against the approaches of other researchers, or even give us some indication, can we apply this model in the real world? Here I listed all that is needed for actually training a neural network. So obviously we need some problem that we want to solve. We need some data set that will allow it. We need to decide on the hyperparameters. Then we use all the free tools that we have. And finally, we need this understanding. What will happen if we change certain hyperparameters? Oof, we went through the theoretical part. So now let's proceed to the live demo. And for the sake of this presentation, we'll pretend that we would like to model this circuit in software. So this circuit is called a first-order diode clipper. It's a distortion circuit. And what it allows us to do is we have the input and we have the output. So this is one dimension in and one dimension out. And the second step that we need is we need the data set. So we have just this schematic, right? So what I recommend doing is actually there's a great website from Fraunhofer IDMT. And on this website, there's already a number of datasets available. Of course, for example, you could record your own guitar and bass as the input signal. But here, you don't need to do this. Basically, all you need to do is choose one. Here's, for example, bass. You can enter and go to download dataset. And you need to simply fill this request. And you're free to use it for research and educational purposes. So that's already a heads up. OK, so we have our circuit. We have the input signal, right? Maybe I can show it here. OK, so the first track here is the input signal. So we assemble different parts of guitar and bass. And we have 8 minutes of audio. Can I play this? That was either, OK. Oh, OK, yeah, try now. Yeah. Perfect. Yeah, that's nice about deep learning in audio, that you actually can listen to your data set. OK, so we have this circuit, right? And we have the input signal. So now, should we solder this circuit and run actually the signal through it to obtain the target? Well, we could do it. But what is much simpler, if we don't want to get into this, there is, for example, SPICE software. And SPICE software is very advanced simulation software that allows you to simulate analog electronic circuits. And of course, if you would like to build high-quality products, it's of course much better to have the real device, measure it, record, but it's quite complicated to do it right. Here we can simply input a wave file as an alternating voltage, and we can get the output wave file as an alternating voltage. And as a result, we obtain the target signal. I need to make it quieter, I think. right, so we have our input, we have our target. Now what? We need to divide it into training set, validation set, and test set. So this is very simple. As you can see, here's our test set, and it's simply a trimmed version of the whole data set in the right proportion. So it's nothing fancy about this. And now we can go and we can arrange it in our code base. So, okay, maybe that's better. So we have the whole data set here. And then the trimmed part I put into the test, train, and validation subfolders, which are all in the data folder. All right, and to make it even easier, what I'm using here, and it's also linked to in the slides, I'm using this core audio ML Python repository as a submodule because it allows us to easily import our data set, have the loss function and networks, etc. So here I'm importing all the necessary stuff, and this is the code that we'll be working with. So we don't need this anymore, and this. So in the first line, we actually say, we check if the GPU is available. And on my laptop, there is a GPU unit, so it will be true. And we say, OK, if there is, then please use it by default. And the next few lines, actually what they do is they read in the data set. And basically what it says is that we have a training set, which should be split into examples of half a second. But then we have the validation and test, which should be just simply one long sequences. And then we read in the files. And then we have this section where we have a couple of constants, which are our hyperparameters. So we have the epoch count. So we'll train for 6 epochs. We'll see the training set for 6 epochs. And then every 3 epochs, we'll perform the validation. The mini batch size will be 64. And this is something new. So when we have the examples of half a second, it will, the network will process a lot of samples after the whole mini batch. So in this case, we want to make the updates more often. We want to do the updates of the parameters every 2,000 samples. And this way, the network will learn faster. All right, so we can write our training loop for each epoch in range from 1 to epoch count plus 1. And believe me, this is easier to write it like this. We train from 1 epoch. So we have network, train epoch. OK, and for this, we obviously need a network. So what we'll have a simple recurrent neural network, which is available in the submodule that I mentioned. And we don't want any skip connections. And we'll say that I hidden size. So we have 8 hidden units, because this problem is not very hard. And then what we need to do, for this epoch, we need to pass in the training data. So we say dataset, subsets, train, data of input 0. And that's our input signal. And then we'll take the same thing, and we'll say we want here the target. And the next thing that we need, actually, is the loss function. And again, it's as simple as writing loss, ESR, loss. So this is this error to signal ratio. The next thing that we need is this optimization algorithm. So how do we want to perform the gradient step? So we need the optimizer. And the optimizer is, again, out of the box in PyTorch. So we have torch, optim, Adam, and we pass it the network parameters, which should be updated, and the learning rate. And you might think that this learning rate is some fancy value, but actually it's the default recommended by the authors of the Adam algorithm. All right, and what we need here is the batch size. We have mini batch size, and the number of samples, which should we update every. All right, and when we've done this, when we train the epoch, it's worth observing what is the loss. So we say epoch over epoch count and loss. And here we have epoch loss. And now, because it doesn't compile right, because this is Python, it's worth always checking if we haven't made any serious mistakes. And that was actually training one epoch. So what we can now do is that we can check if our epoch modulo validate, oops. Okay, perfect. So you see it's learning, right? So we can stop it for now. I say validate every is equal to 0. Then we want to process data. So we don't want to train the network, but we want to process data without computing any gradients. So we can write network process data. And now I'll do something that you cannot ever do, like don't ever copy and paste code. It's a very bad practice. So we change it to validation, right? Okay, and you actually run our validation. To compute the validation loss, we need to pass in the loss function. Maybe this will be clearer. And we can, of course, print the validation loss. And the thing is that if this validation loss is better than the current best, we can store the network parameters. All right. And now when we've done our training, as you can see, we're outside of our loop, we can actually process with testing. This is, again, something you should never do. You should never copy your code. That's a really bad practice. Okay, and now let's simply change it to test. Have test output, test loss, test set, test loss, perfect. But what's actually cool, we are able to now take sound file write, and you can write our test output, and we can listen to how our network performs on the data that it hasn't seen before. And for this, we need to take the test output, we need to bring it back to the CPU, we need to change it to a NumPy array, and we need to flatten it. And then we need to pass here dataset, subsets, test, and something great. All right, so now let me check it, because it would actually be a real pain if something went wrong in these lines. Okay. Looks good. It's always worth to run it, for example, for one epoch and then like see everything, but actually I think we'll take the risk and start training. All right, so while it is training, let me just quickly mention a few things. Here I listed the resources that I recommend, and one of them is Archive, where you can get free papers in the area of deep learning. And the same goes for ResearchGate, which is also an amazing resource. I listed here my master thesis, and not because it's so well written, but it contains exactly this introduction to deep learning in audio, because that is what this was about. And as a conclusion, I would like to leave you with this, that learning deep learning is actually not hard, but what is challenging is successfully training new architectures on new problems and pushing the boundary of research. So this, I would like to conclude. Here's again the link to the slides, the QR code, and if some of your questions are not answered during this session, then please write me an email, and in a minute we'll check on the neural network. But now I would like to ask for your questions. Thank you.